Visualizing Bregman Voronoi diagrams, a joint work by Frank Nielsen from Sony Computer Science Laboratories, Jean-Daniel Boissonneur from Ineria Geometrica, and Richard Nock from USG Cerignia. The Voronoi diagram of a given set of points P1, P2, Pn partitions the space into so-called Voronoi cells Vi of S, such that Vi of S is a loci of points that are closer to site Pi than to Pj, for j different of I. There have been many generalizations of Voronoi diagrams in the past, for objects like points, disks, or handling segments, for distances like considering norms or convex distances, and for order like considering the k-order Voronoi diagram or the furthest Voronoi diagram. This video introduces Voronoi diagrams for Bregman divergences. Let us now define Bregman divergences. Bregman divergences is a family of distortion measures induced from the tail of a Taylor expansion of a strictly convex and differentiable function f. The divergence from P to Q is given by the following formulae and interpreted geometrically as indicating in the figure. Bregman divergences are not necessarily symmetric, and further the triangle inequality may not hold. Let us now give some examples. Consider the strictly convex and differentiable function f of x equal x squared. Then the induced Bregman divergence is a well-known squared Euclidean distance, and graphically it is shown as follows. Let us now consider f of x equal x log x minus x. This is the so-called Shannon anomalized entropy, and the induced Bregman divergence is a Kullback-Leibler divergence that is famously known as the relative entropy. We illustrate again the divergence by plotting the function. Since Bregman divergences may not be symmetric, we define three types of Bregman bisectors as follows. The first type bisectors is always an hyperplane and is shown in blue. The second type bisectors is curved in the primal space X but linear in the gradient space nabla X. And the third type bisector is given for the symmetrized divergence and is in fact a special divergence in X nabla X. Let us now rasterize these three types of Bregman Voronoi diagrams. For the square Euclidean distance, the three type Voronoi diagrams induced by the bisectors coincide, and we have the usual Euclidean ordinary Voronoi diagram. But as we consider non-symmetric Bregman divergence, we can see the relationship between the three types diagrams. The first type Bregman Voronoi diagrams in blue is always an affine diagram. The second type Bregman Voronoi diagram is curved in X but affine in the gradient space nabla X, and the symmetrized Bregman Voronoi diagram is ham sandwich in the first two diagrams. Because the Bregman generator function f is convex, we can use the Legendre-Frenchel transformation to associate to f its dual f star, and it comes that any Bregman divergent d of s has an associated Bregman divergent df star that are linked by the following equation. Observe that here the prime denotes the derivative compared to f, and the arguments swap. Thus, it is enough to consider in the following first type affine Voronoi diagrams. We can also define Voronoi diagrams by considering the minimization diagram obtained from the induced distance function at each site, Pi. By removing equivalent terms in all equations, we find a set of hyperplanes which define a Voronoi affine diagram. This is illustrated in the following figure. To compute first type affine Bregman Voronoi diagrams, we can consider power diagrams for a corresponding set of hyperspheres, with centers already indicated as below. In this Java applet, we show how this equivalence relationship works. On the right-hand side, the circles drawn in red have imaginary radii. The circles drawn in gray have positive radii. Thank you for your attention. You can find more information on Bregman Voronoi diagrams at the following URL website. There are also Java applets online so that you can gain more information on Bregman divergences interactively. Also, the seminal paper was published on SODA, and there's a long technical report available at INRIA homepage under Technical Report 6154. Thank you.